Hello, today we're going to discuss Hardy-Weinberg equilibrium. So, Hardy-Weinberg equilibrium is a principle stating that the genetic variation of a population will remain constant from one generation to the next in the absence of disturbing factors. When mating is random in a large population with no disruptive circumstances, the law predicts that both genotype and allele frequencies will remain constant because they are in equilibrium. Okay, so the thing with Hardy-Weinberg equilibrium is that it describes like this perfect world where life happens, but the thing is that mating is never random, and there will always be disruptive factors with life, because that's just how life works. So there will always be mutations, natural selection, non-random mating, genetic drift, and gene flow. Okay, so Hardy-Weinberg equilibrium shows how the allele frequencies in populations change over time. So, say you're studying a species and a particular gene of that species. So what you do is you have every allele in a population of the species you're studying, you need to have that be tracked and recorded, then you do your Hardy-Weinberg calculations, and then you'll wait a generational cycle of time of whatever it is species you're studying, and then you'll do Hardy-Weinberg calculations again. So when Hardy-Weinberg equilibrium is calculated with different allele numbers than when previously calculated, this means that there was a change in allele frequency over time or evolution. So really Hardy-Weinberg is like a snapshot in time of allele frequencies. Then you wait some time and then you take another snapshot, another round of doing calculations. So mathematically, using Hardy-Weinberg, you can track the changing in allele frequencies over time. You can see where directional shifts are going. So you can see through the numbers evolution happening right before your eyes, which is pretty neat. Alright, so there are two different equations involved in Hardy-Weinberg equilibrium. So the first is P plus Q equals 1. So P is the frequency of the dominant allele and Q is the frequency of the recessive allele. The second equation isn't talking about frequency of alleles, it's talking about frequencies of individuals. So P squared plus 2PQ plus Q squared equals 1, or 100% of the population. So there's going to be a part of the population, or P squared, that is going to be homozygous dominant. There's going to be another part of the population that is heterozygous, 2PQ, and then there's going to be a Q squared, the last part of the population, that is homozygous recessive. Alright, so usually Hardy-Weinberg, what you're doing is you use one equation to find the missing variable and then plug that in to the other equation to figure out the rest of what you need. But it still can be kind of complicated, so I got few practice problems, and by few I mean 3, to help us just understand how to use it better. So with this first problem, we have sampled a population in which you know the percentage of the homozygous recessive genotype is 36%, and we're going to use that 36% to help figure out everything else. So frequency of being recessive genotype, frequency of the recessive allele, frequency of dominant allele, frequency of being homozygous dominant, frequency of being heterozygous, and then what the two possible phenotype frequencies would be if this is happening with classical Mendelian genetics. Okay, working through this problem. So they give us that the frequency of being recessive, homozygous recessive, is 36%. We're going to use that now to figure out just the frequency of the recessive allele. So if Q squared is 36%, or 0.36, do the square root of Q squared and square root of 0.36, and we get that Q, or the frequency of the recessive allele, is 60%. Now that we know Q, we can figure out P, because P plus Q equals 1. We just take 1 minus 0.6 and we get P equals 0.4, which means that the frequency of the dominant allele is 40%. Now we can solve for the frequency of being homozygous dominant. Because we know what P is, 40%, P squared is the frequency of the dominant genotype, so we just multiply 0.4 times 0.4, and we get 0.16, or 16%. And then the last frequency of genotypes is being heterozygous, and that is just plugging in the numbers that we found. So 2PQ is going to be 2 times 0.4 times 0.6, and we get 0.48, or 48%. Lastly, so the frequencies of the two possible phenotypes, if A is completely dominant over lowercase a. So because capital A is totally dominant over lowercase a, the dominant phenotype will show if either the homozygous, capital A, or heterozygous, capital A, lowercase a genotypes occur. The recessive phenotype is controlled by the homozygous, lowercase a genotype. Therefore, the frequency of the dominant phenotype equals the sum of the frequencies of capital A, and capital A, lowercase a, and the recessive phenotype is simply the frequency of lowercase a. Therefore, the dominant frequency is 64%, and the first part of these answers above you already shown that the recessive frequency is 36%. So, what that paragraph says is basically, if having one dominant allele is going to give you the physical dominant expression, we know that the recessive expression is 36%, so we just take 100 minus 36, and we get 64% of the population is going to have the dominant physical phenotype characteristic. Okay, so this problem is more of a real-world application of Hardy-Weinberg. So cystic fibrosis is a recessive condition that affects about 1 in 2,500 babies in the Caucasian population of the United States. Please calculate the following. So the frequency of the recessive allele, frequency of the dominant allele, and the percentage of heterozygous individuals or carriers in the population. Okay, working through this problem. So they give us that the frequency of the recessive allele in the population is 1 in 2,500, or 0.0004. Do the square root of that, and you get 0.02 as the frequency of that recessive allele, which is the same thing as 2%. As soon as you get Q, you can immediately find P, because P plus Q equals 1. So 1 minus 0.02 is 0.98, or 98% is the frequency of the dominant allele. And then you now know P and Q, so you can just plug that in for 2PQ to find the heterozygous individuals. So 2 times 0.98 times 0.02 equals 0.04, or 4% of individuals are heterozygous. Okay, last problem. So the ability to taste PTC or phenyl thiocarbamide is due to a single dominant allele, capital T. You sampled 215 individuals in biology and determined that 150 could detect the bitter taste of PTC and 65 cannot. Calculate all the potential frequencies, so frequency of recessive allele, frequency of dominant allele, percentage of people homozygous dominant, homozygous recessive, and heterozygous. Okay, so first let's go after the recessive, so lowercase t. Since q squared is 65 215ths, that's going to be 0.302, that's rounded. Taking the square root of q squared, you get 0.55, 55% is q. Again, once you know q, immediately just find what p is, so 1 minus 0.55 is 0.45, or 45% of dominant allele frequency. Now, then you're able to find out homozygous, dominant, heterozygous, and then they gave you lowercase t already, which is 30.2%. Frequency of capital T, we know what P is, we just gotta square it, and when we do, we get 20.25% as the frequency being homozygous dominant. And then frequency being heterozygous, again, we know P, we know Q, so 2 times 0.45 times 0.55 is 0.495 or 49.5%.
Thank you for watching. Please share and subscribe, and remember to spread kindness.